So only 9 students are online. So number is quite low. So on this slide number 27, there is a summary given that safe ultimate shear stress. So it is ultimate and safe for no shear reinforcement. So for no shear reinforcement, how much different concretes will have the average shear stress which is considered safe and no shear ties are required. So this is easy to calculate these stresses, because on slide number 27 this relationship was given that it was stated for non-pre-stressed beams minimum area of shear reinforcement shall be provided in all regions where VU will be greater than this right hand side 0.083 times phi. Lambda will remain 1 for normal weight aggregate concrete into under root of FC prime. So you can calculate these values by simply putting 0.083 into phi. Phi is 0.75 for shear, into lambda is 1 into FC prime. So for 17.25 FC prime, so this equation will give us 0.265. So it means if the VU is less than, now we are actually talking about the shear stress. So we will use VU, it is ultimate shear stress. So we will be using capital V for the shear force, and for stress we are using the small letter, and we can use Greek letter to define the shear stress. So when you will put 17.25 here, you will get this 0.265. So if it means that if VU is less than this 0.265, no shear reinforcement is required. So it means for this concrete of 17.25 megapascal and onward up to 30 megapascal, these values are calculated. So for 30 you will put 0.345, it will be replaced with 30, and what you will get out of it will then be 0.349. So this is just one summary that up to how much stress no shear reinforcement are required. So they are actually safe ultimate shear stress, and we term it as average shear stress in the cross section. And we are talking about the 2019 publication of ACI and its equation. Now we want to discuss design equation. Shear strength provided by vertical reinforcement. So I have discussed the diagonal tension crack, and ties, they are, if bridging that crack, they are arresting the diagonal crack. So the shear reinforcement commonly consists of number 10 to number 16 bars anchored against the flexural reinforcement. So I will draw section, suppose it is the longitudinal section, and I'm drawing the section 1-1, which is the cross section of this beam. So in the cross section, ties are present. So flexural steel and hanger bars, if it is a singly beam, are present to hang the ties, and this diagonal crack will appear at this section at this level. So they are actually two legs which are stitching this crack. The shear reinforcement commonly consists of number 10 to number 16. So we normally select the dia ranging from number 10 to number 16, anchored against the flexural reinforcement and hanger bars. These stirrups may be single, double, or four-legged, having the shapes as shown below. On slide number 31, different geometries are shown. Double-legged, which has a seismic hook at the end. Again double-legged, but now it has 90-degree bend against the hanger bars. And it is still double-legged, but in this case and in this case, the fourth loop is absent. So it is not a closed ring. So this one is good enough not only for shear but also for torsion. And thus these two are not good for torsion resistance, because in torsion you will study crack will spiral around the cross section, and each leg will contribute in stitching or arresting those cracks which are spiraling around the cross section about the longitudinal axis of the beam. So a closed loop, a closed tie is more suitable in that case. So when we have monolithic construction and there are T-beams, this So let me resume. So I was discussing different types of shear reinforcement. So two-legged, not only good for shear but also good for torsion. Two-legged, good for shear, good for shear. In monolithic construction, this can be one arrangement that we are having 90-degree bend, and on top the hanger bars or the main steel bars of the slab are engaged to hang the ties. Still not good for torsion because it is open from top. It has four legs. Now when we need more area to resist the shear, we can increase the number of legs. Single leg tie. This is one arrangement in which we are lapping the legs, and this is even good in case when you are actually extending the cross section, and just by overlapping the ties you are actually transferring the stress from one bar to the other. So this can be one arrangement to provide the shear reinforcement. Obviously in that overlapping portion, if this overlap is not rightly calculated, then chances are that a weakened region will develop at this position. However, there are different techniques, and out of them this one is better, not only to resist shear but also torsion. In this case also one of the leg is present on the fourth face, but still there is a deficiency here, so the complete ring is not present in this case. So if I can put one tie like this, it will then improve the presence of the area of steel on the fourth face as well. So in order to handle the torsion, closed loop will be more suitable. So area of steel means combined area of all transverse legs of stirrups at a particular cross section. And I have drawn one picture that if there is a diagonal crack and ties are present which are bridging that crack, so the spacing between the ties will be S, longitudinal spacing, and at one section the combined area of all legs will be the area of steel with subscript V, which is actually contributing at section in shear resistance, and Vs is the shear strength provided by the stirrups at a particular cross section. So if at one cross section we have area of steel, if there are two legs, and as I have shown you on next slide that the two leg stirrup present in the cross section, and in that two leg stirrup area of steel used is number 10, for example, and it is actually anchored against main steel and the hanger bars. So if it is number 10 type, so it means two legs which are actually bridging the crack, diagonal crack, and I'm taking the section 1, which is drawn above. So number 10 has nominal area 71. So since there are two legs which are bridging the crack, 71 into 2. So AV will become 71 into 2. And the shear strength grade of the steel used for the ties, if it is 420 grade, yield strength will be 420 megapascal. So area of legs into the steel grate will provide me the force which is actually resisting the diagonal tension. And if I consider that the horizontal projection of the crack is equal to the effective depth of the cross section, it will be almost equal to the effective depth of the cross section. And that means if a diagonal crack is present and its horizontal projection is D, so what I can calculate that in this span D, how many stirrups are present. For example, in my sketch at the moment, I can say 1, 2, 3, 4 legs are present and stirrups are present, each are having two legs and they are at spacing S. So if this is the area which is engaged in providing the shear resistance, so I can very easily state that knowing both the applied shear force and the stirrups are in transverse direction, it is expected that after the formation of cracks, one shear stirrup can resist equal to AV, area of the legs which are bridging the crack, into its corresponding yield strength. And the average resistive force provided per unit length of the beam then becomes the force divided by the spacing between the stirrups. So it is like if I am using the force units kilonewton and spacing in millimeter, so it will be kilonewton per millimeter, because I am dividing AVFY, which is AVFY will be force divided by spacing. So I am actually calculating the resistance per unit length. And if the dimension of the crack is assumed to be equal to effective depth in longitudinal direction, then the shear strength provided by the stirrups Vs will become force per unit length into the distance on which crack is present, and we have assumed that dimension as D. So it means how much steel force will be offered, it will be resistance per unit length into the length of the crack, which is equal to D. So in this picture I can say that first I have calculated per unit length, then I multiplied it with the distance on which crack is present. So this will give me the resistance, shear resistance, shear force offered by the steel. So AV actually will be decided based on how many legs are present which are arresting the diagonal crack. So in this above picture, we have 71 into 2 because there are 2 legs. Shear strength reduction factor, according to ultimate strength design, we will be using is 0.75. It is relatively lesser than the corresponding factor in bending, so it gives more factor of safety. Firstly, due to sudden nature of failure, and secondly, the reason of having more stringent reduction is the larger scatter of the test results. So even in 2019 publication, still with the proposed equation which is used to predict VC shear strength offered by the concrete, still the capacity reduction factor applied is 0.75. There is no revision made. Now in the previous recorded lecture, I mentioned that if VU is lesser than phi V into VC, theoretically no reinforcement is required. So I have given you that equation on slide number 27, that is phi into VC, which is 0.083 into under root of FC prime BWD. So now it is again mentioned here on slide number 33 that if VU will be lesser than this, theoretically no web reinforcement is required. It means actually when the ultimate shear is less than the capacity of concrete alone to resist that ultimate shear, and we are using 5.75. However, to keep safety in mind, in case even if VU is less than 5V into VC and theoretically no web reinforcement is required, however, code will recommend you that if VU is greater than or at least equal to half of this 5VC by 2. So even if it becomes greater or at least equal to half of the capacity of concrete alone, the ACI requires the provision of minimum area of web reinforcement. So actually the equation on the slide, this one is actually phi VC over 2. So if your VU is less than half of the capacity of concrete or maximum equal to this, then there is no requirement of the minimum area of shear reinforcement. However, if it exceeds even half of the capacity of concrete, and still it is less than the capacity of concrete, but it exceeded half of it, then code is suggesting, considering factor of safety because shear failure will be greater, that provide minimum ties with area not less than, by using these set of equations, and from both of them larger will be selected, and it means I can write equation like this, that VU is greater than phi VC by 2, but it is still less than 5 VC. So it is greater, or even it will become equal to half of the concrete capacity, but it is less than the concrete capacity. So theoretically speaking, shear is still less than the concrete capacity, and ties are not required, because if VU will exceed 5 VC, then we will have a surplus shear which we want to shift to ties. But still, if the VU is less than 5 EC, code will recommend you to provide minimum ties if VU will exceed half of the concrete capacity, but it is still below concrete capacity. But if it remains below half of the capacity, then you can ignore provision of ties. If and only if VU is less than or maximum equal to half of the concrete capacity alone. But if it exceeds, then we need to consult these set of equations, and out of them larger we are going to select to detail the shear rings. And it is further mentioned on this slide that the second expression governs. You will have to apply both of them. Actually, on the left hand side equation, FC prime is present. So once FC prime will get bigger and bigger, the left hand side will start getting more value, and right hand side involves steel grade, width of the cross section, spacing between the ties, while the left hand side equation also involves the concrete grade with under root of FC prime. So it is mentioned second expression will govern, which is actually the right hand side equation, when FC prime is below 31, or you may say about near about 32 megapascal. But if the shear concrete grade will improve, then left hand side equation will start governing. So you have to check both of them, and out of two, larger you will select. It is important to note that the maximum spacing limit, it is also very direct recommendation that I have shown you on this picture. The spacing between the ties, code has recommended that the spacing between the ties should not be wider than half of the effective depth. So even when you calculate spacing, and if it is exceeding half of the effective depth, you need to reduce the spacing to half of the effective depth. So it is important to note that the maximum spacing limit of d by 2 is also required to be satisfied for this minimum web reinforcement. So once you will calculate the web reinforcement from this equation, so idea is that either you will put AV first. For example, I decide that I will keep S as unknown, and I will put AV first, and according to that AV, what spacing this equation gives me. For example, if I decide that I am putting double legged number 10 stirrup, so I am putting this 2 into 71 here, that equation will then give me how much is the spacing between the ties, where minimum requirement is governing. So if this spacing comes out to be greater than d by 2, I have to provide the spacing not exceeding d by 2. So this is one choice. Second is that what spacing you have decided d by 2, you will put over here. You know the effective depth of the cross section, and you will put d by 2 over here. What is the code maximum limit, and according to that you will calculate AV minimum. So I will apply these equations in the problem, and you will then understand how we can check that our detailing is according to the code recommended, either in terms of spacing between the ties or with reference to AV minimum, which is required in the region where VU is greater than half of the concrete capacity but less than concrete capacity alone to resist shear. Exceptions where this minimum reinforcement is not required are members that have capacity to redistribute stress across the width of the member, or in some cases to adjacent members, having following examples: slabs and footings, concrete joist construction. So these bullets under are already explained on slide number 27. So that when you have cases where AV minimum is not required, those cases are already summarized, so you can read them, because at the moment we are only discussing reinforced concrete beams. So there are some exceptions which are summarized, which you can review later on. And one more important thing which I want to discuss before starting the solution of problem, that for non-pre-stress sections located less than a distance d from the face of the support may be designed for same shear Vu as that computed at a distance d. So what does it mean? I will discuss this from this picture, that code will recommend you to determine the shear force at a distance d, which is d is actually the effective depth of the cross section. So you can move to a distance d from the face of the support, and at that section shear force, what you will calculate will be the design shear force, against which you will check that this VUD is greater than phi VC or not greater than phi VC. So actually the design shear force is not at the face of the support. You can move to a distance equal to the effective depth, and this shear force will be considered as the design shear force. What is the reason? For reason, this picture is good to understand. Look at the beam in which load is applied on top, and imagine if it is a monolithic construction, there will be a flange over here, the slab which is present, and on top of it load is present. So the load which is present within a span d from the face of the support will be transferred directly to this support, and this load has no effect on the stresses over a crack, while the load which is away from distance d from the face of the support, this load or the shear force at this distance will actually be affecting the stresses over the crack, and the ties which are going to resist that force will actually be taking the share of the load which is beyond the distance d from the face of the support. So these ties are actually taking the share of that shear force which is beyond the distance d, while this force will go directly to the support. However, if it is inverted beam and slab is present at the bottom and slab is being uh, loaded with the pressure, now you can see that the diagonal crack is almost over here, and whatever is the load present on the slab, it will go directly to the column and very close to the face of the support. Now the contribution is by the slab to be transferring load directly to the column, while the critical section, if you compare this picture, the critical section was at distance d, while in this case the portion of the load which is transferred directly to the column is very small, and we can consider then that in case of inverted beams, our critical section will come to the face of the support. Rather, it is uh, at a distance d from the face of the support. So it is actually the case that you need to look at the condition that where is the slab present and what critical section will then be. If it is a normal beam and slab is on top, then you need to move to a distance d from the face of the support. But if there is a inverted beam, then critical section will be at the face of the support, because all the stresses on the crack will be taken by the ties, and the distance up to which the load will contribute towards the stresses over the diagonal crack will be the total span of the beam. So we will then move it to a distance, not to a distance d from the face of the support, but the critical section will be exactly the face of the support. There are few more pictures. In this case, again, slab is on top, shown shaded, and we are moving to a distance d. Here in this case, again, monolithic construction, frame joint, column and beam. Although here there is no monolithic construction and we have a isolated isolation or a bearing pad between the beam and the column, but still the diagonal crack will form and the load over here will go directly to this support, and on the crack it will not affect the stresses. Here again the same case, but if it is a frame construction and we have integration of the beam with the column, but within a distance d from the face of the support, there is an unusual concentrated load present within the distance d from the face of the support. Then we need not to be moving to distance d. We have to then take the critical section at the face of the support, because in this case it will definitely affect the stresses over the crack when we have some point load or a reaction within the distance d from the face of the support. If your beam is framing into a member which is subjected to tension, again in this case the critical section will not be at distance d from the face of the support, it will be on the face of the support. So such guidelines are present, and I have copied this picture from ACI code. You can find some more pictures in that document which I have shared with you. Now one more important information, that how much maximum stress we can pass on to ties. It is not a, you can say, a permission. There is no permission that I will be transferring the surplus shear to ties without taking into account that how much maximum Vs is permitted by the code, because if we will transfer more extra shear to ties, it will result into widened cracks, and we need to have the crack widths minimum. So there is a limit given on Vs, and that limit is 66% of under root of Fc prime. So if the stress will exceed this on the shear rings, we need to then change the cross section, because we want then to have more VC. So more VC we can get by either by increasing the compressive strength of concrete, or otherwise by changing the cross section. So we need to check it first that whether our cross section is good enough, and if Vs will exceed this value, we need to revise the cross section. So this check we will be doing right in the beginning, when we will calculate the share of the shear force to be transferred to the ties. And when Vs, the shear on the steel ties, does not exceed half, which is actually 0.33 under Fc prime BWD, is actually half of that section suitability. Actually, it is section is suitable if your Vs is less than or maximum equal to 0.66 under Fc prime, and if your Vs is equal to this or maximum equal to this or less than this, it means on the slide number 39, it is actually Vs divided by 2. On 39 it was 0.66, and it is actually half of that. So if your Vs does not exceed 33% of under Fc prime, then maximum allowed spacing between the ties you will calculate by these set of equations, and out of them smaller spacing will be selected. And in addition to this, the fourth equation will be the design equation, which we have discussed, that we will calculate based on the equation that AV Fy into D over S. So we have done this assessment on the previous slide. So what we will do, we will have these three set of equations, and furthermore, if our Vu is greater than phi Vc, it means we will then have a surplus shear, and we will say Vu minus phi Vc, and the additional we will then transfer to phi Vs. And that phi Vs, which is the now the share of the steel, we will be calculating it by one equation, which will be in addition to these three, 1, 2, 3. So these are direct equations which are not involving what is the actual demand and the resistance offered by the concrete, and what is the surplus force which is to be transferred to the steel ties. So this is the actual design requirement, and that we are going to calculate by one additional equation. You can put fourth one, and that is discussed on the next slide, and I will talk about that equation, how to derive it. So when Vs exceeds, so it was when Vs does not exceed this 0.600 Fc prime BWD, but if Vs exceeds this, so let me write it like this, that Vs is less than 0.66 under root Fc prime, which is the upper limit, into BWD. I can also put less than or equal to, but it is greater than 0.33 under root Fc prime. So the shear on steel rings, if it will exceed this 0.3 Fc prime BWD, but it is still less than the upper limit, which is to decide whether the cross section is suitable or not. So it is well below or maximum equal to this, cross section will still be declared suitable. And now Vs is in this range. Then the three equations, direct recommendations, are little different, and smaller of the following three will be selected. First one is the same as it was on slide number 40, but second and third now reduced to half value. It was d by 2 when Vs was less than or equal to 0.33 under root Fc prime BWD, then it was 6d by 2 or 600. Now since it exceeds 0.33, now it is dropped to 1/2 of that. So one, rather than d by 2, it is now d by 4. Rather than 600, now the requirement exceeds and the spacing drops to 300, half of that previous recommended. So spacing between the ties maximum should be smaller out of 3, and we will also put the fourth one, which is the actual design requirement, and that is explained here. Now what I mentioned, that you have the nominal shear Vn, you multiply it with phi to get the ultimate. So this will be our equation according to ultimate stand design, and this phi Vn we are going to replace it with the ultimate demand, ultimate shear force. So since, as I mentioned, that if Vu is greater than phi Vc, so what will happen then? It will be Vu minus phi Vc, and then on the right hand side it will be phi Vs. So what we are going to do then is we are going to calculate based on that surplus demand what is the spacing required. So I have given you on that slide that what was area of rings which are bridging the crack, AV, of steel grade Fy, and they are at spacing S, and they are present over the length of the crack D. So this was the I would say the Vs, the force offered by the steel. Now I will put reduction factor along with that phi, and on that also I will put a capacity reduction factor phi, because we are working on ultimate stand design. I will bring this S on the left hand side, and I will bring phi Vs as the denominator on the right hand side, and it will also be multiplied with this capacity reduction factor. Now what this phi Vs is, it is actually that surplus shear force which is extra to that which is offered by the concrete. So I will put in the denominator then AB Fy d over Vu minus phi Vc, and it will be multiplied with the phi. So this will give me actual demand of the spacing between the ties, and this spacing, which will be based on actual shear force demand, if it exceeds S max, which is given as direct recommendation 1, 2, 3, and out of them smaller one, I will have to follow the smaller. So for example, if this gives me a spacing 200 millimeter, this gives me spacing 100 millimeter, this is a direct recommendation 300 millimeter, and the fourth equation gives me 150, which is the actual demand. I have to provide the ties at a spacing 100. So the fourth equation, although is the direct demand, I may call it equation 4, which is based on your actual requirement over the crack, and based on that what spacing you need to provide that resistance. The size and number of legs of stirrups should be selected to avoid spacing making the pouring of concrete difficult, and it is also recommended that the spacing between the ties should be taken not closer than 80 to 90 millimeter. In some cases we may even go up to 75, but below 75 millimeter, obviously less than 3 inch, there will be too much congestion and coarse aggregate flow will be obstructed. So we should avoid uh, such situation. In that case, if our demand of S is uh, decreasing and we are having the very closely packed ties requirement, then option is that we can increase the number of legs. By increasing the number of legs, it means our AV will increase. If I have 2 legs, I will make them 4-legged, so AV will be doubled, and then obviously in this way spacing will increase. We can manage that by increasing the number of legs. Typical shear force diagrams. I think you all are expert in drawing the shear force diagrams. In the continuous beam topic, I will discuss that can we get a simplified answer to that shear force values in continuous beams. Otherwise, you know, movement distribution, slope deflection methods, you can apply them on continuous members to draw the shear force diagram. Now it is a flow chart which I want to skip, and because I am going to solve the problem directly, And finally, once you will go through this example problem, you can read later on the flow chart that will help you to further understand the solved problem. So this example problem is in SI units. So I will also share with you one problem from book by Nadeem, 7th edition, and it's also in SI units. So both example problems are good to understand the flow chart of the shear design of beams. Now, in this example problem, what they are talking about is a simply supported beam. So there is no monolithicity between the support and the beam. So beam is resting on RC column. So I am showing double hatched to represent that there is no monolithicity between the support and the beam. So it is simply supported end condition. Beam has a clear span 4.5 meter and imagine that the support width is 300 millimeter on either side. 300 by 300, right? So if I want to determine center to center distance, so it means it will become 4.5 plus 0.15 from either side. So it will then become 4.8 if I am talking about center to center distance. Clear span is 4.5. So you are expert in plotting shear force and bending moment diagram. To plot bending moment diagram was mandatory when we were applying the one of the equation proposed by ACI in 2011 publication and also even in 2014 publication. But now in 2019 publication, they have provided more simplified equations. So calculation of movement diagram or application of movement diagram in estimation of VC is now no more required. So earlier codes required calculation of M because in our equation M was also present. Just to give you one you can say hint about this, I mentioned that in 2011 publication there was equation which involved MU, but now I am actually applying 2019 equation. There is no MU involved in calculation of VC. So it means movement diagram is as such not important in calculation of VC now. So they have now directly given you some multiplying factors along with the reinforcement ratio and the concrete grade. So in one other equation, the size effect is incorporated by giving you one coefficient lambda s. So as such now it is more simple to determine VC by following the current ACI code equation. So as we discussed that in this case now load is present on top, you can imagine that there will be slab over here if it is a monolithic T-beam. Even if it is a rectangular beam, load is present on top and the diagonal crack will form. So the load up to a distance d from face of the support will have no contribution over the diagonal crack stresses and it will be transferred directly to the support. So it is recommended to determine the design shear force by moving to a distance d from the face of the support. So we are not actually interested in the shear force as the design force at the face of the support. We are interested in shear force at a distance d from the face of the support. And we can write the shear force equation. As I said, moment equation is now not as such important if we are applying the 2019 equation. So our shear force diagram, by moving a distance d from face of the support, and d in this equation is in this beam is given that a simply supported beam of size 300 by 525. It is the gross dimension of the beam having an effective depth of 450. So for this beam, they are providing you not only the cross section, which is 300 by 525, but also the effective depth. So 3525, and it has been stated that the clear span 4.5, effective span center to center 4.8. The flux reinforcement consists of 8 number 25 bar. So what they are providing you, that you have in this beam 4 plus 4, 8 number 25 bar. There are two layers of steel and each layer has 4 number 25, and finally the effective depth they have provided you by subtracting the cover from 5 to 5 is 450. In addition, obviously on top there will be hanger bars, maybe of dia number 6 or number 10, and then the ties are actually enveloping. So this is the cross section they are providing you. Flux reinforcement consists of 825 US customary, 4 of which are curtailed at 450 short of face of the support, and concrete and steel grades are also given, and they are also suggesting you to use double-legged stirrups. So that is the reason I have detailed it as double leg. So one leg and second leg. So it is a double-legged recommended tie. There is some idea given regarding the curtailment, so that I can explain on this picture as, so that I will discuss when I will be talking about bar bending schedule. Just to give you idea, I am drawing on this beam first layer of steel which is penetrating inside support to a distance 150 millimeter from face of the support. It goes in, and recommended distance by the code is 6 inches, 150 millimeter. The reinforcement must enter the support for simply supported beams even. The second layer, what they are recommending you is that the second layer, which is again 4 number 25, you can curtail the bars, you can cut the bars before reaching the support, and you can cut them at a distance d before the support, the second layer. Why they are doing so? Because you know that movement diagram is parabolic. So this steel required actually is at the support, at the midspan, which is 4 plus 4. So as you move away from the midspan, your movement is dropping. So strictly speaking, against this section, your movement magnitude is relatively less than the mid-span maximum moment against which you design two layers of steel. So that is the reason we normally curtail bars where the moment demand reduce. So that will be our topic in PRC2. Here they are actually talking about that you have two layers and they are recommending you in statement that the second layer is being curtailed before the support to a distance equal to the effective depth of the beam, and effective depth of beam is actually 450 millimeters. So this is one idea given to you by the statement. Now shear and movement at the critical section, since we stated that we will move to a distance d from the face of the support to get the design shear. So what will be that? 312 reaction minus 130 into our effective depth is 0.45. So when I will subtract from the reaction which is at the center of the beam, so actually yeah, there is one more point which is important. Since in this question they are taking x from center, so they are calculating this 312 not corresponding to 4.5, they are calculating this 312 corresponding to center distance. So 130 into 4.8 divided by 2 is actually 312. So in order to move to a distance d from the face of the support, first I have to travel to a distance 0.15 from center to the face and then further 0.45. So total distance which I will travel in order to get distance d from the face of the support will then be sum of 0.15 plus 0.45, because I have drawn the shear with reference to center. So that is the reason over here this x will be actually 0.45 plus 0.15. So when you will put this x over here, you will get VU D 234 kilonewton. Now since we are not using 2011 publication of ACI, so this is now meaningless. I am not applying that equation. However, in the latest 2019 code equation, rho W is still present. So that I am going to calculate. Now, in calculating rho W, don't forget that this two layers of steel is present at the center, right? And at distance d from the face of the support, they are cutting the second layer. So strictly speaking, rho W at distance d from face of the support, your reinforcement ratio is actually with reference to one layer of steel, because half of the steel is curtailed. So that is the reason they are dividing the total area of steel, which is 8 number 25 bars, by 2 to get the reinforcement ratio at a distance d from the face of the support. Now I will not apply this equation because as per the latest ACI code, I am going to apply the equations which are present on slide number. Let me just take you to that slide and I will remember that number so that I can quickly jump to that slide. Yeah, slide number 25. Now I'm going to apply them when AV is greater than or at least equal to AV minimum. When AV is less than AV minimum, it means when no steel is present, no ties are present, you will use this to calculate VC. And when ties are present, you will calculate either of A or B. Now these equations I'm going to apply for my problem. And I mentioned in my video lecture that there is no axial force in this beam, so this second component will be 0. So I am using these equations to get the VC. It is mentioned either of, so I can use any one of them. So there is no requirement greater of or smaller out of them. Any one of them, it is our choice. So it is on slide number 25. Let me go back to my slide where now I will call this equation. First equation of 2019 tells me that VC is 0.17. I need your help to apply those equations. So this is one of my equation which is present in the current code, and I may call it equation A. It is along with BWD, and in the second set of equation it was VC equal to, we will put phi as well later on, it is just nominal, 0.66. That was the second set of equation. Lambda is the lightweight aggregate factor, so it will remain neutral. Then there was a rho W with power 1/3. Then there was FC prime into BW into D. So there are two equations present on slide number 25. Let me take you to that slide 25. So I have reproduced them. 0.66 lambda rho W FC prime under root, either of them. So can you help me? That first equation gives us how much our you can say concrete grade is 20. So 20 megapascal is FC prime. Can you calculate from equation A how much is VC? It is 0.17 into lambda 1 because it is normal weight aggregate concrete into FC prime 20 into BW 300 into D 450. So what I get from equation 1? So can anyone calculate VC in kilonewton? Divide your answer with 1000 to get answer in kilonewton. So please respond to me quickly. Section D. Point 17 into 1 into 20 under root into 300 because BWD is 300 by 450. And answer I am calculating in kilonewton. So I am dividing it with 1000. Please open your mic and tell me.
Sir, 102.64.
102.64. You are replying in
64.
kilonewton. Good. In kilonewton, right?
Yes, sir. Kilonewton.
Now, can you give me the answer from equation B? Your rho W is 0.015 because I'm calculating it at the distance D from face of the support. So rho W is 0.015. Let me rewrite it for you. 0.66 into lambda 1 into 0.015 with power 1/3 into 20 into 300 BW into D 450. So it was stated either of. So can you give me the answer of VC from this second equation?
Sir, 98.27
Good.
kilonewton.
98.27. So if you just compare it with the previous ACI set of equations, previous equations were giving you 108. Now this seems to be more conservative. One is giving you 102, other is giving you 98. So if you compare 2011 with 2019 equations, you will find that the latest code equation is giving you the prediction of VC even more on the conservative side, yani ke it is decreasing the resistance. Now you can select any one of them. There is no restriction that you will select greater or smaller. So what do you prefer? We can go with this 102.64. No issue at all. Let it be 102.5 just to round up to a reasonable value. Or if you think 98.27 is more safe, conservative, you can select this as VC. Now don't forget, sorry, don't forget that the latest ACI equation also recommends that the VC what you will calculate shall not be taken greater than this. That is the upper limit. And just to get that upper limit, can you confirm me that if I calculate this for our beam 300 by 450, what is the maximum PC what we can take as per 2019 code? We should not be selecting above this. तो ये कितनी आती है जी?
Sir, 253.2.
Oh my God. So it's too much above. So no issue at all. We are well below that upper limit. So in that regard, I may suggest you that for our problem, we can very easily take 102.5 kilonewton, if not
5.
agreed. So from this slide onward, this will be our VC. So in your books, if you will follow the previous edition of Z.A. Siddiqui or McGregor or Wilson, you will get these equations which are present on the slide, which I have now crossed. But even if you will attempt your problem with the previous set of equation, I will not mind. But it is always advisable to follow the new set of equations because better prediction is based on latest research and better equations are proposed. So it is now 102.5. Fine. So I will keep on modifying it. 102.5 you have selected as BC. So multiply with 0.75. So what is our latest 5 EC as per our latest code? कितना बनेगा जी? 5 still 0.75. CR 102.5 into 0.75. Because now we are multiplying the nominal with the phi.
Sir, 76.88.
76.88 is our 5EC, and we need half of it because we want to apply all the you can say equations. So it is recommended that check whether your demand is greater than half of the concrete capacity. So 76.88 divided by 2, how much? 2 3s are 6, 2 8s are 16, 38.44.
38.44.
Okay, so now a little drop in the 5EC and 5EC by 2 is taking place with the latest equation. Now, what is our VU? VU you have calculated at a distance D from the face of the support was 234 kilonewton. On this slide, you have calculated the design shear at distance D from face of the support was 234. We are actually in a situation that neither it is below this nor it is below our capacity. It is well above both the limits, because it was suggested that if VU is less than 5 VC but greater than 5 VC by 2, you have to provide the minimum stirrups. But if it is less than 5 EC by 2, then no stirrups. But in our case, incidentally, we are not in this ideal situation that our VU is less than the concrete capacity alone. Our demand is quite high, and that 234 minus what concrete alone can offer, which is 76.88, gives me how much? Surplus shear, which will be transferred to steel as 5 VS
157.12.
157.12. So this is actually 5 ES now, what will be taken by the steel. And I will bring that phi, it is actually 5 ES, which is equal to 157.12. But I will bring that phi as denominator on the VU minus 5 VC, which is 0.75, to get how much is VS, because I need to check that my VS is how much, because if VS will exceed this, I need to revise the cross section. It was suggested by court that your what maximum you can transfer to the ties should not be above 0.68 FC prime, and if it is above 0.33, there were strict requirements of spacing. So what 157.12 divided by 0.75, what gives us VS, which I want to compare against these two limits. So please tell me what is VS by dividing.
Sir, 209.5.
Good, 209.5.
0.5.
Good. So incidentally, when I calculate 0.66 FC prime BWD, I am satisfied because 0.66, which is the cross section suitability, in that requirement I am pretty okay with the demand transfer to the steel ties, because 0.66 into 20 under root will give me quite, into BW 300D 450 will give me quite high value, which can be transferred to the ties without any problem. But when I check 0.33 under FC prime BWD, I get the idea that this limit is 199.2. But incidentally, my VS is greater than 0.33 under root FC prime PWD. So I'm in a situation where I mentioned on this slide that if my VS will exceed this, then the requirement is 1 D by second, D by 4, third 300. So in that way, I am little careful that my VS 209.5 is greater than 199.2. So cross section wise dimensions are okay because it is below 0.66 and FC prime BWD, but it is above this 0.33. However, it is stated VS is greater and specific limits are to be used accordingly. And what are those limits? 1, 2, 3, and 4th our actual equation. So I decided that I will be using 2-legged number 10 tie. So it has one leg of area 71. So into 2, it will become 142. So S max should be smallest out of the following 4. First one gives me 379. D by 4 gives me 112. Journal minimum 300. And the equation what we have calculated from our latest equation is 209. VU minus 5 EC, what we have calculated was 157.12. So it is 157.12 because VU minus 5 EC is this. So it will further reduce. How much it is? How much it is? CR. Anyone else? 0.75 into 142 into 280 into 450 divided by
Sir, 85.4.
good, 85.4. So let it be 85 round value because it is easy to measure during layout, multiple of 5 or multiple of 10. So 85 millimeter. And in this problem, even against 88, they are suggesting to round up to multiple of 10. So 80 is suggested. So first stirrup code recommends to put at distance half of the spacing, 40, and then onward 80, 80, 80. It means the first will be at 40 and then all others are at 80, 80. Since your shear force diagram is that it is reducing, so at further some distance away from the support, if shear dropped to a lower value, we can select any other section at some distance further away from the distance d from face of the support, and against that we can calculate the latest requirement of spacing, because this 80 actually is exactly at distance d from face of the support. So constantly you are seeing that there is a linear decrease in the shear. So strictly speaking, at every slice away from the section at distance d from face of the support, since shear force is decreasing, so you can increase your ties, but practically after every you can say tie, we can't change the tie spacing. Practically such layout will be quite tedious and saving will not be too much. What we do, we normally keep that spacing constant to a reasonable distance until we get a reasonable drop in shear force, and then at that section again we calculate VU, and then we repeat the same flow chart. We calculate 5EC, we subtract and we call the 4 set of equations, and out of them we calculate S. So in this way, in this problem, the next spacing what was recommended was 150 until you get to the center of the beam, or until you get to a section where your VU will become less than 5VC by 2. So when your VU will become less than 5VC by 2, theoretically speaking, you need not to provide ties. So that is the reason in this problem, they have selected that section where your VU even drops below half of the capacity of concrete. So ACI recommends that you can ignore provision of ties where VU drops below half of the concrete capacity. And in this problem, they have taken two different shear forces because it was linearly decreasing. So at further distance, 80 millimeter away from the face of the support, a second section was investigated, and against that the spacing comes out to be 150. And don't forget that even if you get spacing, and that spacing should not be wider than d by 2. So it is the minimum, it is the maximum recommended by ACI code, that your spacing should not be wider than this. So in this way you can see the remaining part of the problem, which is solved one. In addition to that, I recommend you, since I have shared with you on Teams folder this book by, it's 7th edition by Nadeem, and in this book, when you will go to shear and diagonal tension chapter 5, you will get one problem in SI units. The good part is a very good example problem, complete problem discussed by author on page 184, example 5.5, and he has solved this problem, complete one, by calling the latest ACI 2019 publication. So please attempt this problem at home. In that way you will understand all the checks which are required. We have also checked AV minimum, that area steel nowhere where we need minimum requirement of ties would be designed below AV minimum. So that check he has also applied. And then finally the distribution of stirrups is discussed. So in next lecture I want you to solve this problem at home and also bring it in, you can say, in soft form, or you can take pictures of your solved problem and then share it on MS Team folder as assignment, example 5.5, and also attempt this complete problem which is present in the slides from the slide onward where I stopped solving the remaining half of the problem. So I stopped at 80 millimeter, which was the first from the support at distance s by 2. The first tie is provided, and in this presentation you will find that they are using the previous equation. So wherever they are calculating VC from this equation, you need to discard it and you need to calculate the VC from the equations present on slide number 25. So in this way you need to repeat this problem. It is more easy now to calculate VC. What you need is you need VU, latest VU, what you will use to compare it with the VC from the equations given on slide number 25. So in this way, for the next portion, they have calculated the spacing 150. If you will provide the same spacing 80 millimeter throughout, it means you are doing over design, because here was actually linearly decreasing. So you should reduce the spacing between the ties. You should increase the spacing between the ties, because actually shear force dropped. It was linearly decreasing. If you have a beam in which the shear force diagram is constant, like there is a point load in the beam, and you have for that beam the shear force diagram like this, then obviously you need not to change the spacing of the slides, because shear force remain constant. But in case of uniformly distributed load, you are having the linearly varying shear diagram. So since shear force is decreasing, you can widen the spacing between the ties. So in this way, shear force diagram will decide that what is the magnitude of shear, and corresponding to that, what will be the tie spacing along the length of the beam. So at this point, I will stop my today's lecture. So only 24 students are online present. So this video was recorded and it will be uploaded on MS Team. So I'm just going to stop